Hello, students! We are going to move on from the beginning of learning about the periodic table to studying it in more depth and looking at electrons. There are a ton of things you can learn about electrons. We're going to go over a whole lot of stuff really quick. I'm going to try and give you an introduction so that as you read your textbook and watch other videos, it starts to make more sense. I want you to know that fundamentally what you need to know for the rest of the class about electrons is what is in your valence, which means the outer shell of electrons. But understanding how they build up and where they are is important just to have a conceptual idea. So give it a shot this week. Try and absorb all the tons of information you're going to learn. Do a little bit of practice with the worksheets. But then fundamentally at the end of that, say, do I understand what happens in those outer shells of electrons? So let's get to it, all right? First of all, we've talked about electrons so far as if they're a little particle. We draw a little circle, we say it's a little thing, it has a little bit of mass, and it's here maybe orbiting around something else, right? I even used my example here of my little ball, right? So if I were to say this is hydrogen, I'd say we have a little bit of a hydrogen electron that's moving around this hydrogen nucleus, and that's totally not exactly really what's going on. So have any of you learned in physics about the particle theory of light? We learn with light, there's a wave theory, and you can do some experiments and totally prove that light is a wave. And then later they came along and they started doing some experiments and they totally proved that light is a particle. And then you start to say, wait a second, how can it be both? What's going on here? And eventually, with our understanding of science, we say that light is both a particle and a wave. It has this duality. Well, electrons are the same thing. I don't have time to get into the deep science of it, but electrons behave both as if they are a particle and as if they are a wave of energy. Really fundamentally, when you get down to it, energy and mass are the same thing. Matter and energy are just different forms of the same whatever stuff, right? And so you have to just accept it and learn to understand it better. However, that's not really going to affect what we learned today, but I want you to understand that that's part of the reason why we have these quanta. Remember, we talk even in atoms, but also in electrons about we have certain packets of energy, and it can't be just anything in between. It's either here or it's here. So we have been talking about that that's how they developed the whole atomic theory, that atoms as the smallest element of matter were certain amounts of something. Well, we're also going to talk about that with energy itself. So let me draw a little diagram of an atom. Now, again, this is not representing what an atom really looks like, but I want you to understand, okay? So let's say we have an atom, and this is the nucleus, and it has some sort of positive charge, and we have some electrons out here in what we're going to call a shell. That's not super nice, but we're just going to say we have an electron out here in the shell. So what they learned is scientists built a machine that called a spectrograph, and they were examining elements way before they even knew atomic theory with this spectrograph. And a spectroscope. I'm sorry, it's called a spectroscope. Anyway, they would use a spectroscope, and just like it was Newton who first analyzed light and saw that you could divide light into different colors to make a whole spectrum. Remember, we talk about the electromagnetic spectrum. But they would burn an element and shine a light through the spectroscope, and they would get lines of color at certain frequencies. And they learned that they could determine exactly what an element was by the particular lines that it put on the spectroscope. And this was one of the beginnings of learning about atoms. What is interesting is that they learned if they gave more energy to an atom, it might bump up a line somewhere, but it would bump in certain specific amounts or quanta, right? So when we go back to this atom I'm talking about, we have this shell of energy, but if you bump an atom up or an electron up, you have an additional shell outside that. And then there's another shell outside that. And I'm drawing these as circles, and this is super messy, I realize, because I went right off the page. But I want you to think about the fact that these electrons can bump themselves up from one to another. And if they do, that takes energy to move an electron up from one energy level to the next energy level. You have to put energy in, for example, heating something up, or some other example. And then you can move an electron perhaps up to another energy level. When that electron then goes back down to the previous level, if it bumps back down, it gives off some amount of energy, which is usually light. and we can detect that light, okay? So all of this led to the development of more knowledge about the energy levels of an atom. Now, this is a pretty ugly diagram, but I want you to understand that there were these, exactly what I said, quantum levels of energy. It's a bump up from one to the other. It's not a whole sliding spectrum in between. What we developed from that knowledge is a knowledge that the electrons themselves try and fill the lowest energy level spot, basically. They have these places where they want to be around a nucleus. And that the electrons will fill the lowest energy level first, and if you add more electrons, they fill the next higher levels and the next higher levels of energy in this atom, okay? So let's look at our our hydrogen, right? We have one proton, one electron. Oh, I need to draw this much smaller. I don't know why I always try and draw it so big. Let's draw one electron right here in hydrogen, right? Well, that one electron is all alone, but when you add helium, or when you go to helium, we add another proton and some neutrons. We now have two electrons. They're going to be in that lowest energy level. So electrons always want to fill that lowest energy level first. Then after that first level where there's only two electrons, we bump up to the next level. And the next level, this is what we will eventually draw, but the next level is going to show, and actually this is very typically done like this, so I'm going to draw it more the way we usually do. We're going to say there's an electron here, an electron here, in that n equals 1 energy level. The next one, we're going to say it first wants to put the same two electrons in there, and then it goes up and adds 6 more, which I'll talk about more later, but we're going to say we add 6 more. And this is what we call the valence, which equals the outer. Valence is your outer electrons, or outer shell. Whatever electrons are in the outermost shell. So that first shell was the 2. The second shell has 8. You see that? And then we're going to go to another shell, and it's also going to have 8 in it. And I drew it too big, you can't see it. But we're going to keep adding to these valence shells. And at the end of this whole week, when we go back, we're going to be looking at those 8s and those shells about how they react, because it's really the electrons in that outermost shell that are going to react with everything else around it. Okay? So you want to know how many electrons are in the outer shell. That's what you really care about most of the time when we start doing chemical reactions. All right. Having said all of this, though, we're going to go back. I'm going to add a new page here, and we're going to draw something completely different. So let's talk about those energy shells. So we're going to say that lowest energy level, we call it n equals 1. It can have 2 electrons in it, right? Well, that next level, where we go to n equals 2, it can have a total of 8 electrons in it. When we go up to the next level, n equals 3, we can have a total of 18 electrons. Now, why did it jump up to that? Well, we're going to have to start talking about energy levels, which we're going to call shells. Then we're going to talk about subshells, and we're going to talk about orbitals. All right? This is more actually how an atom works and looks. And so I don't want you to get too confused, but I'm going to dive in, okay? So there's a lot of vocabulary, but we're going to say shells are equal to these levels 1 through 7 that I was just talking about. So n equals 4, n equals 5, and I don't know why they use n for number instead of like s for shell, but that's what they do. And n equals 7, okay? And you have a theoretical maximum number of electrons that you can have in each shell. And these fill in order, and it's all really nice through level 4. After this, we start getting kind of more theoretical because they don't behave exactly like you'd expect, because these electrons, when you're getting tons and tons of them, they're so far away from the nucleus that the forces don't hold them as tightly, and they can start behaving weirdly. But we have 50 that could possibly be there, then 72 and 98. All right, so that's how many electrons could technically go in each one of these energy levels. But within each energy level, we have something that we call subshells. Now, subshells have letters. And these letters come from way back when they were doing those spectroscopes and they were seeing lines on a piece of paper. And they were based on what those lines looked like a solid line or a dotted line, or not dotted, but it was something like that. So we're stuck with this convention that is S, P, D, and F. So we call our subshells, and sometimes it's easy to get the notation confused, and people might call these orbitals, but technically they're subshells. So S, P, D, and F subshells. One way you can remember this is just to say, some people do fine. That's our SPDF. Some people do fine. Okay? To remember your subshells. And they fill in that order. All right? Underneath those subshells, we have orbitals. And basically, an orbital is 2 electrons can fill an orbital in each subshell. Now, each one of these different types of subshells has a different shape. So let's start with basic. Let's say the very smallest and most basic subshell is this S subshell, and it has a spherical shape. So I could draw a circle and say, this is the shape of the subshell, and you can have 2 electrons in it, right? So does that mean they're out here and they're orbiting? Well, actually, what it means is you have a likelihood that somewhere within this, let's call it a cloud, that's a spherical shape, you are going to have the 2 electrons are going to appear somewhere in that cloud. And if I draw it, it's going to look maybe more like this. Like they're more likely to be in the middle. They might be out here. And the likelihood of them being further out is even less. Imagine these are all dots, right? So it's really like a cloud, and it's a likelihood of where that electron is. Now, when I say is, either that, if we're talking about a particle, it would be a physical location, but it might be sort of an energy wave, and where does that energy reside, okay? Or where is it highest? And so that is the more true representation, but we're just going to draw it as a circle for now, okay? So I'm going to erase this and say this is an S orbital. Looks like a circle. P is also not too hard. Usually they call it a dumbbell shape. It really looks more like this. So the P orbital means you might have, electrons somewhere in this cloud shape. Now a P orbital, you could have 2 lobes sticking out sideways. You might have some sticking towards you and one behind you, and you could have one up and one down. So what that means is you might have an electron here, an electron here, one here, one here, and this one sticking towards you and one back. Do you see that there are 6 lobes if you have all of these P's filled? And that's how many you can have. A P orbital can have 6 electrons. Remember, we said an S orbital can have 2. Now, what about these D and F? Well, D gets to a whole lot more complicated shapes, and you'll see that in the literature. They can have things like this with like a donut around the middle. And F gets even more complicated with like double donuts. Or you might have 4 lobes all sticking out different directions. Same thing with D's. I'm not drawing it very well, but you'll see some pictures. Anyway, these are all just likelihoods that something might be there, okay? So it's just a cloud that you might have something in. Having said all of that, there is this whole complication of where the electrons go, but I'm going to try and bring it down and make it simpler, because the electrons, as you add them to an atom and make a new element, they're always going to fill the lowest energy level first. So what is the lowest energy level? Well, let's get a new page. Let's start fresh. We're going to say the lowest energy level, 1, can have, and I'm going to draw this as a box because we can have one box can have 2 electrons in it. And the electrons have to have opposite spin. So we draw that as an up arrow and a down arrow. So this would be helium has 2 electrons. The second level will have 1 S. This is S. And remember, we talked about some people do fine. Some people do fine. So the second level can have 1 P as well. And that's going to have 3 boxes in it. Okay? So as you add electrons, you're going to add electrons here. And then you would add them. Actually, they always go alone. So you'd have 1 each direction in the P. And then if you add more, they'd start adding the other direction. Okay? So that's going to be your level 2. When you get to level 3, you're going to start adding this D orbital. And remember, the D, I can't remember if I told you already, can have 10 electrons, or basically 5 boxes in it, right? So if you're filling it, if these were all full, whoops, I drew that one wrong. You would start filling the D. Okay? And then you'd start filling with the down spin. And then you would eventually get to level 4, which would have all of them. This one. And then it has F, which I didn't draw enough space for. Okay? It's going to have 14. So you'd have 7 boxes, which you could have one up and one down. Okay? So this is called the electron orbital diagram. When you draw it this way, it's an electron orbital diagram. And it's basically really just showing you where the electrons are in each one of those orbitals. And it's just a graphical representation to help you know where they are. Unfortunately, this isn't the way we usually write it. In like literature, if they're trying to show you where every electron is in an atom, what we use instead is called an electron configuration diagram. Electron config, wow, that didn't work. Configuration. Oh, it's called notation, not diagram. Sometimes my pen gets ahead of my digital. There we go. Notation diagram. And in this case, what we do, you'll see something that looks maybe something like this. It'd be like 1s2, 2s2, 2p3. Now you'd say, what in the world is that? Well, this is the shell. This is the orbital. Subshell. See, I do it too. Subshell. And this number right here is how many are in the orbital. So that's how many electrons are in this orbital. Which is basically, the orbital is like that box I just showed you in this diagram. Each of these boxes is like an orbital, okay? So if I look at this one, you can say there are, I'm going to draw this in blue, there are 2 electrons in this S, 2 electrons in that S, and 3 electrons in that P. So that means there are 1, 2, 3, 4, 5, 6, 7 electrons in this atom. So what is it? Well, I can look over here and say, if it's 7, this is nitrogen, assuming it also has 7 protons, which it should, because we're just talking about a basic, where are these electrons going? So we use this notation to write down where the electrons are so we know which orbital they're in which energy level. Okay, so this is like an unexcited atom. What energy level do they go in? You can imagine as you get up to these bigger and bigger atoms that this notation is going to get super long. And what they eventually do is they take the noble gases over here and they say, we'll write the noble gas in square brackets, and then we'll write everything that comes after it. So maybe if you're down here, you'd say, well, that's krypton plus everything to get to that point. Okay? I hope that that's clear enough. You'll have a lot more instruction this week in both your text and in other videos about how to do this. The easiest way really is to do, there's a diagram where you write 1s, and then you write 2s, 2p, and 3s, 3p, 3d. And then anyway, you're going to use some diagonal lines to know what energy goes first, because that one's the first and then that one's the second. But 2p fills and then 3s before 3p. And then you're going to keep going and it's going to be 3p, 4s. And then 3d is going to fill before 4p. And so you use this diagram. I haven't written the whole thing out, but you'll use that diagram to know which energy level each of these electrons goes to next, okay? So I hope you don't get too confused by this. How does this really relate to the real world, though? What do you know? I want you to look back at, we're going to look back at the periodic table and say, what does this mean, okay? So you notice the first orbital, the first energy level, 1s, has 2 electrons. Well, that's hydrogen and helium. Okay, this is your level 1s. Well, the next level, you have 2s. Well, that's these two is the 2s. And then over here, you have a 2p. 1, 2, 3, 4, 5, 6. You notice that fills you out to 8 electrons. This one was 2, right? Well, now let's go to 3. We have got 3s, 1, 2. And then we have 3p. 1, 2, 3, 4, 5, 6. Do you get it? Isn't that cool? Well, you might have remembered that I said the third level had more than 8 electrons in it. Well, that's because this level right here, if you can see this box I'm drawing, those 10 across, that is your d orbital. But 3d is this one right here. So we go to 4s, but this is 3d that comes next. So you're going to fill 4s and then 3d. That was the crazy diagonal diagram I showed you. But here you can see it on the periodic table. This is where your electrons are going to go. They're going to fill this up first. Then they're going to fill the d orbital of the level 3 energy, right? I mean, they're going to fill the s subshell of the level 3 shell. Excuse me. Got to say my shells right. And then we're going to go over here, and this is going to be 4p. Okay? So this block right here, this is S. This block right here, this is P. This block right here is D. And this crazy block right here, which really fits in right there in the middle, is your F orbital. I hope that makes some sense of this. I realize it was confusing because I threw a ton at you really fast, but I hope that it helps you get started with what you're about to learn this week. Having said all of that, let's go back. Remember how I said what I really care about in the end is more like this diagram right here, where you're looking at how many are in the outer valence. You're going to learn all of this, but then we're going to apply whatever's in this outside shell. It wants to be 8. So it's going to do reactions with anything else to try and get something that acts like 8 electrons in the outer shell. And that's what we're going to learn when we start looking at different chemical reactions. Now, there's one more thing I want to define for you that you might not know and you'll come across in this lesson, and that is ions. An ion, we learned about isotopes where the number of neutrons was different in the nucleus. Well, an ion is where you have an atom that has a different number of electrons than it has protons. So ions are going to be either an atom that's lost some electrons, perhaps to keep a nice 8 in the outer shell, or gained electrons to keep 8 in the outer shell. And those are called ions, and they will have a positive or a negative charge based on whether they have added electrons or subtracted electrons. So in this lesson, when someone refers to an ion, that's what they're talking about, is more or less electrons. And if they refer to ionizing energy, that's that energy bumping up or down that I talked about. We get ionizing energy by creating or an ion or going back to not having an ion, whether you add an electron or whether those electrons get bumped up in energy. That was a super fast overview of everything that you're going to be learning this week. Good luck. Have some fun. It's really fun to kind of learn this notation. Don't let it stress you out too much. Just decide that, hey, this is a cool puzzle I get to solve, and I'm going to learn the rules. All right? Have a great time this week. Thanks.